All right, the natural exponential function. We're going to use your calculator for this lesson. What I strongly encourage you is to not just copy it off of the video, but to actually go through this stuff yourself. You need to know how to do it, and it's not enough just to watch it. So what I want you to do first is use a calculator to find the following values. So we go over to y equals, type in your function, and then remember our table set, and you can look it up in your calculator handout. We want to make sure that's on Ask. And then we can go over to Table, and I have the values typed in there. And so we just need to record those. 2.5937, 2.7048, 2.7169, 2.7181, and 2.7183. Now the question I have for you is, what do you think is happening to these values? Are these things going to keep on getting bigger? They're getting bigger, but they're only getting bigger by a little amount here. Do they keep on getting bigger and bigger and bigger, or is there a value that it won't go above? If I keep on going, I can keep on pressing some bigger and bigger numbers out in this. It turns out that there is what we call a limit. Now this is red, and we're not going to get into limits big time right now. We're just going to introduce it a little bit. The limit as n goes to infinity, so the limit as n gets really, really big of this expression, 1 plus 1 over n to the n. And it turns out that this number is e to the 1, which is approximately equal to 2.71828. So what it's saying, let's actually just write that down. The limit as n approaches infinity of 1 plus 1 over n to the n is, not approximately, is e. This is an equal sign for the e. E is approximately 2.71828, but this limit is exactly e. Now let's go over calculating the amount of money in an account. If you're starting with $100 and you compound it, whatever it says in each part, and we have 12% annual interest. So let me do the first one for you. We have 12%. We have our growth factor is saying we have 1 plus 0.12 divided by 1. This is what we've been doing. We have 1.12. How much money do we have in the account at the end of the year? It'd be 100 times 1.12, or 112. Now, for right now, I'm just going to tell you this effective annual yield is this equation. And later on in problem 4, I'm going to show you really where that comes from. So we get the 112 minus our starting amount, 100 over 100, and we get equals to 0.12. And what that means is we have 12% for that year. And we already know that. That's what we were given here. But it's going to change when we do these next ones. Try to do these next few things by yourself. We have semi-annually. We're going to compound this interest semi-annually. So that means we take 12 divided by 2. It means we get 6% each 6 months. Okay, so twice a year we get 6%. Now the benefit of this is we're going to get the 6%, and then when we get the second 6%, it's going to be interest on the interest we've already received. This is the beauty of compounded interest. So over here we'll have 1 plus 0.12 divided by 2, and we get 1.06. Now what we're saying is we have 1.06 is our growth factor. How many times are we going to compound this in 1 year? We're going to compound it twice. So it'd be 1.06 to the 2. And you do that calculation, you get 112.36. And then we can just come over here, 112.36 minus 100 divided by 100. So we get 0.1236 we get an interest rate this time of 12.36%. So that interest is a little bit better than what we had if we just compounded annually. So now we need to do this again quarterly. How many quarters are in a year? We have 4 quarters in a year, so we'll take our 12%, divide it by 4, and we get 3%. So that's saying each compounded period we get a 3%. We'll take our growth factor, 1 plus 0.012 divided by 4, and we get 1.03. Now this time, we have 100 times 1.03 to the what power? Well, how many times are we going to compound this in a year? Well, we're going to do it 4 times. Do that calculation, we get 112.55. Now we'll compute our effective annual yield, the 112.55 minus 100 over 100, and we get 0.1255, which means we have now 12.55%. Monthly. Now we're going to go 12 divided by 12, and we get 1%. So our growth factor would be this time 1.01, because it's 1 plus 0.12 divided by 12. And we get 100 times 1.01. Now, how many times are we compounding this? 12 times in 1 year. And in the next problem, we'll start talking about if you have more than 1 year. And this is approximately equal to 112.68. And then compute the effective annual yield. And we get 0.1268, which gives us 12.68% now. You see, every time the percentage is going up, it's not going up a big deal, but over time that makes a huge difference. Daily, what's this one going to be? Now we're going to compound it 365 times. 365 is in the day, so we're not going to simplify this. So our growth factor will just be 0.12 divided by 365, and that plus our 1. Remember, our 1 stands for 100% of the original. Now when you do this kind of problem, what we're just going to do is plug it in, and we're going to use our calculator. What's our exponent going to be? How many times are we compounding it? 365 times. And this time we get 112.75. And again, we compute our effective annual yield. And we get 12.75%. Now what I want you to do, especially if you haven't done so far, stop it and try to do k times a year. What's that going to be? All right, this is going to be 12 divided by k is our percentage. So our multiplication factor, our growth factor, would be 1 plus whatever k times per year is. Now what's going to change on this one? What's our exponent going to be? We're going to raise it to the power of k. Now, let's take a look at what this means when we talk about continuously. Continuously is all the time. So not just every day, not just every minute, every second, all the time. How many times are we really compounding it here? Well, there's an infinite number of times. What we're going to need to do is find a limit. And it's a limit as k goes to infinity of 100 times 1 plus 0.12 divided by k raised to the k. Now, have we ever seen that before? Yes, we did this in problem number 1. What we want is this form. We want 1 plus 1 over n to the n as our expression part. And this 100 is something we can just leave alone. We're going to bring it out in front. Our goal right now is to take the 1 plus 0.12 divided by k raised to the k and transform it so it looks just like this. So we have the 1 part in plus, but we need 1 over something, okay, raised to that something power. So how do we get this and make it look exactly like that? We can say 1 plus, if we want a 1 on the top, we could find the reciprocal of this thing. So in other words, what we're going to do is find the reciprocal twice. Because if you flip, reciprocal is flipping a fraction, and if you find the reciprocal again, you flip it again, you come back to the original fraction. So this fraction is equivalent to the original one. We put 0.12. Now what we need to do is have this exponent the exact same thing. So for right this moment, I'm just going to write it in there. We want k over 0.12 and k over 0.12 as our exponent. But now I just changed the problem because our exponent is really k. What can I do to this? To counteract this 0.12, I can multiply by 0.12. So I can raise this as a power of 0.12. Now what we're going to do is say let n equal k divided by 0.12. And one thing we're going to need to do is think about this. As k goes to infinity, what happens to k over 0.12? So as k gets bigger and bigger and bigger and bigger, and you're dividing by 0.12, what happens to n? Well, n is also going to go to infinity. So now let's take a look at this. I'll pull this 100 out, and that's one of the rules for limits. And we're not going to spend a lot of time again on limits right now, but this is something that is good to know. This is going to be 100 times the limit as n goes to infinity of, well, what do we have here? 1 plus 1 over n to the n raised to the 0.12. Now this isn't such an easy thing to look at and figure it out. I understand this. But what happens here is this part here is going to give us what we got in problem number 1. That is e. So it's e to the 1 raised to the 0.12, so it's just e to the 0.12. And what you could do is take out your calculator and type in 100 times e, and your e button is 2 keys above your on button, and 0.12, and what you get is approximately 112.75. Now I want to point out something. Let's take a look and compare that to the daily. They are approximately the same. If we looked at some further decimals, they're not exactly the same. Our book will say, oh, if it says or daily, just use continuously. I don't want you to do that. If it says daily, I want you to use daily. If it says continuously, I want you to use continuously. All right, let's take a look at the next page. So let's summarize this stuff as to what is going on. I can look at that part right there that we just did. In general, if the rate is being compounded continuously. Now, some of the words that you'll see for there is that, and we'll write this down in just a second. This is, actually I'll just do it right now, continuously or all the time. And sometimes we're going to have to determine whether or not it is that. So if it's continuously or all the time, what we're going to do is have this situation right here. So we have P of t equals P sub 0 e to the RT, and P sub 0 is what? That's our initial amount. You could also call it your starting value. What is R? Or actually, we can go T. T would be here the number of years, and R would be our rate as a decimal. That's key. You got to make sure that you're converting that to a decimal, because otherwise you're going to get some outrageously large number. What were these parts? Well, P sub 0 was, again, our starting amount, our initial amount, either way. T is our number of years. Now, it is possible, though, that you could have different time units. In fact, you could have different time units over here. But it could be number of months. You have to look at the context of the problem to determine that. If we're talking about the money being compounded, then we're saying it's annual. R would be our rate as a decimal. And what is K? K was the number of times compounded in a year. Now it has to be that, again, we're dealing with the money, so that would be the compounded in a year. So let's take a look at a problem here. Find out how much each of the following plans yield. Which plan is the best? And this is just to go over what we just did and the formulas we just came up. All right, we don't know the starting amount, so we're going to call this A sub 0. Now, we're going to compound this annually, so it's only one time per year. We have a 1. That's our 100% of the original. 0.075 is our interest rate, and we want that whole thing. It's only one time a year. Now, we're going to do this for 6 years, so how many times are we going to compound it? Well, if it's done once a year for 6 years, we have a 6. So do that computation here. The only thing we're really looking at is A sub 0, 1 plus, actually 1.075 raised to the 6. Type it in on your calculator, you get 1.5433 times A sub 0. So it doesn't really matter what A sub 0 is. What we want to do is look, what's this number in front of it? Now we'll look at A sub 0. This time we're going to compound it monthly. So we have 1 plus 0.072 in this problem. So it's a slightly different, slightly less rate, but we're going to compound it a little more, and we'll divide this one by, since it's monthly, 12. And now, how many compounded periods are there in 6 years? Well, we're doing it every single month for 6 years. How many months are there in 6 years? It'd be 12 times 6. Type that in on your calculator, and you'll get A sub 0 times, actually I'll just put the number in first, 1.5383 A sub 0. And we need to go out to 4 decimal places so we can really see what's going on here. And this last one, A sub 0, what's the key on here? You want to notice that it's continuously. So as soon as we see that, you got to go straight to E. And our rate would be 0.07. And our time, type that in on your calculator, put this whole thing as our exponent. And this is approximately 1.5220 times A sub 0. So which plan is best? Well, it turns out this 7.5% is the best plan. After a year during which the interest is compounded quarterly, an investment of $500 is worth $532.50. What was the effective annual rate? What I'm going to do right now is show you where that formula came from on the previous problem on the other page of the notes. So what this problem is really looking at is saying, all right, we're going to start with some initial amount, $500. The way it's compounded really doesn't matter. It doesn't matter if it's quarterly, daily, monthly, whatever the case may be. What it's saying is, given that it's been compounded and it gives you this as a net result, what would the interest rate be if it were only done one time during the year. If you were only given interest once for the year, what would that annual rate be to get the exact same result? So we'd have 500 times 1 is our 100% plus the rate for that we're looking for, and it's an annual rate, so it's only going to be R. Now note, we've done problems where I've done it as 1 plus R, and we've also have done it as 1 plus R over 100. It doesn't matter which way you write it, just be consistent in the problem. Raised to the 1, because we're talking about 1 year, and this is going to equal $532.50. To solve this, it's easiest to divide by 500, so 1 plus R equals 1.065, so R equals 0.065. And that's telling us our interest rate is 6.5%. Now let's take a look at it in general. We have a starting amount, P sub 0, times 1 plus R, and we're dealing with this right now over 1 year, equals P sub t. To solve for this, divide by P sub 0. So we get R equals P sub t divided by P sub 0 minus 1. And if we have a common denominator, this would be P sub 0 over P sub 0. So we get P sub t minus P sub 0 divided by P sub 0. And that's the exact equation that we had on the other side. That is the effective annual yield, or effective annual rate. Now the only difference, what if it was over multiple years? Then we might have an exponent, or we would have an exponent here. And that's it for these notes.